Because if you've dug yourself a hole, it's on you. All right, so how would you set up finding the molality? What are the units for molality? Anybody? So I hear you say moles of solute, kilograms of solvent. Okay, so for this first example, who's the solute? Who's the solute for A? Sugar. And who's the solvent? Water. Okay, so I literally tell you 2.3 moles, so no conversion needed, of sugar, which is sucrose. And water has to be converted to what? So how do you convert? Divide by 1,000, so 3 decimals over, so that's 0.5 kilograms of water. So what's that molality? Sorry. 4.6. You just multiply by 2 when you divide by 0.5. 4.6 molal. Okay. Is sucrose ionic or covalent? Covalent. Sucrose is it's like glucose, C6H12O6. So C, H, and O. Those are all non-metals, so that's how you know it's covalent. I'm going to make a note here because we're going to utilize that knowledge in just a second. Okay, so for B, how do you get to molality? Convert grams to moles, and then how many grams is this? 750 grams, okay? Nothing fancy. 1 milliliter of water is equal to 1 gram of water, so it's really easy to just go convert, right? So, it's blue, it's a little easier to see. So this right here, 131.0 grams. What's barium nitrate? So you'll notice I'm not going to give you the formulas. You are okay at nomenclature. Some of us are better than others. You got to keep working on it. What's barium nitrate's formula? NO3, 2. So then taking that to moles is 1 mole of barium nitrate weighs what? You guys got that? 261.4 grams. Okay, so then that's like half a mole, right? 0.5 moles. Okay, that's 0.5 moles over what? 0.75, right? Kilograms of water. So I don't know what that is. 0.66, 0.68. Okay, 0.68 molal. 0.68 molal. Okay, is that one ionic or covalent? Ionic. How do you know? Just by looking at it. It's a metal. If it's got barium, it's a metal. It's in the front. We got ionic substance, right? Okay, so barium nitrate versus sucrose. So we have sucrose, which I'm gonna write it as glucose just for your basic knowledge. C6H12O6. Barium nitrate is ionic. Ba parentheses NO3 2. How many ions does this break into in solution? Did you hear me say ions? Hold on. Did you hear me say ions? Is that ionic? If it's If it's not ionic, it does not make ions. Is it ionic? No. So how many ions does it break into in solution? 0. So it stays as 1 molecule, yeah? It stays as 1 molecule. So how many, when this thing's dissolved in water, how many particles do they make? It's kind of the new way I'm going to say this. How many particles does this make in solution? 1. It's going to stay as 1 because it can't make 0 because it's something, right? It is literally a molecule. It's staying as 1 molecule, okay? So we're going to call that something called the I factor. I is like particle number, okay? So I hope that you're listening to this. I'm probably not going to teach this part a whole lot again. This one, when it ionizes, because it's literally ionic, it can ionize in solution. How many things does it break up into? 3. How do you know? Right, there's 1 barium and there's 2 nitrates. So this breaks into barium 2+, because that's the charge of barium. And how many nitrates? 2 nitrates. Do not be a homewrecker and break nitrate up. It's a little happy family polyatomic ion. Don't break it up, right? So you have 1 of these, 2 of these, so its I factor is 3. So ionics always make more particles than covalents. Yeah. I factor, we're going to call it Van 't Hoff factor in notes today. It's just some guy's name. But it's just basically telling us the number of particles that it breaks into in solution. So sodium sulfate, formula? Here SO4, okay, but what am I missing? 2, Na2SO4. How many particles does that break into solution? Tell me specifically what it makes. 2 sodium ions, because there's 2 here. Yes, put a parentheses around sulfate to remember it stays together. There's a 1 there, so plus 1 sulfate. 2 minus is its charge, so it makes 2 plus 1, so its I factor is 3. Let's do one more, just for kicks and giggles. Calcium chloride. Cl. Chloride. Ide always ends with what the periodic table says, which is just chlorine. But what's missing? 2, so how many ions does that break into? 3, okay, because there's 1 there, 2 there, 1 and 2 is 3. Okay, so basically if I give you something covalent, how many particles go into solution? 1. If I give you something ionic, break it up and count it up. Okay, so we're going to talk about that in a picture form, and then we're going to do some calculations with it today. So you can see, these are just more examples. Sodium bromide, calcium chloride, ethanol. You see this is like a molecular model form. It's not an ion form, so this looks like a big honking molecule. What would this break into? 1. It would stay as 1, right? This would go into 3. This would go into 2. All right, so that's how we have to talk about different solutes breaking up separately. Which of the examples earlier, sodium bromide, calcium chloride, or ethanol, which of those would be electrolytes? Why sodium bromide and calcium chloride? Okay, so ionic means breaks into ions, or can break into ions. Electrolytes, what does that kind of sound like? Electricity, so they can help do what? Conduct electricity through solution, right? This is a lot of review right now, okay? So, conductive ions in solution. Basically, they can conduct electricity. You can see my little battery over here lighting up. So then the non-electrolyte would be which of these? C2H5 OH, because it's covalent. That's like alcohol, so it's non-conductive. Non-conductive, so we cannot conduct electricity with ethanol. Okay, so if you got this, quick review, let me know, thumbs up, and I'll move on. Alright, so was there anything really new today except for the I factors and so far? Okay, so I want to go through colligative property notes so that we can practice that in class today. I have a couple people that have to leave me shortly, Jamie and Josh, to watch the video. Colligative properties are some of the most interesting types of properties we talk about. So what are some properties we've talked about, Grace, throughout the whole year? Properties. Like physical properties of compounds.
Solids.
Okay, so there's state of matter. What else? Jamie, what else? Properties we've talked about this year. So we've state of matter. Come back to you, Alex. Boiling point. What else? Malleability, conductivity. What else? Ductility. What else? Anybody? Melting point, freezing point, boiling point, volatile, odor, color. You can talk about all kinds of properties, right? So now we're going to talk about properties of solutions, and solutions have 2 components to it. What? Solute and solvent, right? Everything we've talked about this year so far has been about just the solute, like ionics are, high melting point, high boiling point, stuff like that. And then just the solvent, like just water. Well, water's got a kind of high boiling point, 100 degrees Celsius, high specific heat. We've talked about everything separately. Now we're pulling them together to make a solution. And when we pull them together to make a solution, they have totally different properties, okay? So we're going to talk about everything in respect to the solvent, okay? So the physical properties, colligative properties, are physical properties that we've always talked about, like, for example, melting point, boiling point, and so forth. But they change the solutions. They change their properties once we put the solute in it. So now we're kind of meshing 2 ideas. meshing two ideas, the solute properties, the solvent properties, and seeing how they influence each other. This is probably the most writing you'll do. No, not this one. Okay, so I'm going to start here and I'll work my way down here, okay? So we've talked about solutes having specific properties, solvents having specific properties. The solution has now changed properties once you've combined those two things together. And so what we generally call these things are colligative properties. It's like a combined property. But it's not really dependent. It's dependent on the solvent that we're playing with, but it's also dependent on the number of particles going into solution. Okay, so that's what we work through. How do ionics dissolve? How do covalents dissolve? Because the number of particles is going to cause a bigger change. Basically, if you increase the particles, increase number of particles, it causes a bigger change in solvent property. So whatever the property is, we're talking about boiling point, freezing point, vapor pressure, it just causes a bigger change. So you have to be able to count up the ions, or say, molecules stay as one molecule based on what it is given to you, okay? So the identity, like specific identities don't matter, but it does matter if it's ionic or covalent. That's the kind of broader general picture. So the three properties we're working with are vapor pressure lowering, and I'm going to consistently just call this VP down, so vapor pressure lowering, freezing point depression, and boiling point elevation. So you're probably really familiar with freezing point and what freezing point means and what boiling point means. Vapor pressure we talked about a little bit, so I wanted to give you a quick review definition of vapor pressure before we kind of start delving into details about it. Is it okay if I scroll down? Yeah. Do I need to scroll up at all? Okay. Yeah. Do that. Okay. So vapor pressure. Vapor pressure is equal to atmospheric pressure when something is boiling, okay? So vapor pressure is actually related to boiling point. So whenever I think it was Chris was my atmosphere when I was trying to boil, and he was playing atmosphere pushing down, and I was playing boiling trying to push up. When they're equal to each other, the solution or solvent or whatever it is, it will start boiling, right? Well, if the solvent's not able to create a lot of vapor, well, the atmospheric pressure is continually going to be able to win, okay? So the vapor pressure that's caused by a solution is just basically due to evaporation of that liquid. If the liquid can't evaporate, well, there's less vapor pressure. So low evaporation equals low vapor pressure. Just finish watching the video later, okay? And I'll walk through all the colligative property questions on the lecture notes. There's like 6 of them. Okay, so low evaporation means low vapor pressure. And then give me a big cheesy smile when you're done here. You don't have to. Big toothy. Give me everything. Because I want to show you how this relates to boiling point in a second. All right, I'll go to the middle here. All right, so if I am the water trying to boil, and I lower my vapor pressure, I'm not going to be able to push up as much, right? So Emily, be my atmosphere. Be my atmosphere. Push on the water here. Okay, so atmosphere is pushing on the water. If the vapor pressure of the water lowers, it's not going to be able to push past the atmosphere, right? So it's lowering. Once I get to the point where the vapor pressure is so low, I'm going to have to heat that thing up hot. What does that mean I'm doing to the boiling point? Raising it or lowering it? Raising it. So the vapor pressure is so low, I can't push past it, right? So the only thing I can do is heat up the water beneath so I can finally push past the atmosphere, okay? So basically, the vapor pressure lowering causes the boiling point to have to elevate, aka increase. If not, it will never boil. So vapor pressure lowering and boiling point elevation, they're directly related with each other. They're one causes the other, okay? So now let's talk about each of these individually. I have some pictures that are really helpful. Okay, so vapor pressure lowering, I'll go back later. Vapor pressure lowering will be, what we kind of just talked about. So write down what you need to here, but we kind of just talked about a lot of it already. So you can see the vapors forming here, the atmospheric pressure is pushing down. So these two will become equal eventually, and then it will boil. And then here, you can see there's less vapors. Basically, there's less vapors because down here, the blue stuff is pure liquid. Pure liquid, and this is pure liquid with solutes. It's almost like the solutes are distracting the solvent molecules, and it's causing them kind of stay in solution. So if the solutes are distracting, kind of basically they're interacting via IMFs. If they're interacting, then the solvent cannot escape, cannot form vapors, so therefore there's lower vapor pressure. So that's a picture that kind of helps again with the decrease of vapors leaving solution. Decrease the pressure which vapors escape the solution. I'm not going to dwell on this much more. Kind of like killed this one now. We have to conceptually know this one. We will not do calculations with this one. We'll do calculations with the boiling point one and the freezing point one in just a moment. But vapor pressure helps explain other things. So basically the solutes are interacting with the solvent. Solvent can't leave. If solvent can't leave, solvent can't cause vapor pressure. Okay. Freezing point depression. These are examples you should know that relate to freezing point depression. So which of these are we going to deal with tomorrow? Ice cream. So I'm getting milk and sugar and vanilla. If you want anything extra for your toppings, that's up to you to bring. I do have some sprinkles. That's pretty much all I have. Yeah, sprinkles. Sprinkles are the best anyway, right? So these are 3 different examples you should know that relate to freezing point depression, right? So basically, you have a solvent on the road, or that helps make ice cream, or in your radiator. What solvent's generally on the road? Or solvent, not solute. Water, ice. Ice is water, right? So the solvent water, it will normally freeze at what temperature? Right. Freezing point is generally 0.0 degrees Celsius. So what they do is they put salt, lots and lots and lots of salt, or brine, soap brine, salt, road salt, all these different types of words for this. They put it on the road. So as the water molecules, we saw how ice looked. It had a kind of a hexagonal. This is going to be a hexagon. I think that's a pentagon. Let's go hexagon here. Okay. It's kind of got a hexagonal appearance when the ice forms, right? Well, what did I tell you was in the middle there? Nothing. Okay, there's nothing there, right? Well, when I put salt on the roads, this salt is going to start interfering with this lovely hexagonal formation, so ice can form, right? So if salt is a home wrecker and it gets in the middle of it, can the water freeze? No. Okay, so the water is trying to, it's slowing down, it's lowering temperature, it's slowing down. The salt's getting in the way. They can't form ice crystals. Eventually, it's going to get, -5, -10 degrees maybe. And eventually, the water molecules are moving so slow, they actually kind of just stop in place and they make their little hexagonal arrangement. But it's because we've gotten them so slow, so like low in kinetic energy. So the salt is basically interfering with the freezing process. So we call that freezing point depression because it's lowering the freezing point down to like maybe -10. So does North Carolina really hit that? No. We've hit 0. That's, it's not hard. 32 degrees Fahrenheit. It's not that bad. Not that low. So we can hit freezing point, but if they want us to come to school, they're going to put salt on the roads. They're going to lower the freezing point so we can all come to school. Yeah. Okay. So same thing with making ice cream. We're going to lower the freezing point of water. We'll put milk in a bag. The milk starts to freeze. It makes a yummy dessert. Okay. So you can kind of see it stops the formation of ice crystals, and then this is a joke. Friends keep you from freezing. Non-volatile solutes keep the water from freezing. Okay, boiling point elevation. So this one's going to be one that relates to probably something you've seen in your own kitchen before. Food cooks faster if salt is added, but the food has to be cooking in water. In what situation in the kitchen would you add salt to water? Spaghetti. Let's see if I can spell spaghetti right. Looks right, yeah? Spaghetti. It's like the hardest word to spell. Okay, so spaghetti, you have water and you put salt in it. Why? Well, it is supposed to help them not stick, but I'm thinking more about the chemistry. What are you saying? It's not that it sucks up the water. Okay, so water is naturally going to boil at 100 degrees Celsius. Okay, yeah. Okay, it does raise the boiling point. So why do I care about that in the kitchen? Okay, but also, have you guys ever had the experience of boiling water and it boils over? Okay, and it smells really bad because you get some of the burner and stuff. So water boiling over with spaghetti is a bad idea. So the spaghetti in the water, it's starting to boil, it's boiling, 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 you get that foamy top and it comes out at the top of the pot. Well, that means it's hitting about 100 degrees and it's starting to boil and it's coming out of the pot. If you want to maintain your water in your pot, you put salt in the water and it increases the boiling point to like 102, 103 degrees Celsius. So that's like, 220 Fahrenheit, whatever that is. So it's going to increase it so it doesn't boil out and over. Hey, it does cook the spaghetti faster too. So it kind of serves two purposes. So the new boiling point would be like 102 degrees Celsius. Okay? So it's based off the solvent of the water. Now the freezing point depresses a whole lot faster than the boiling point elevates, and you'll kind of see that throughout the work through today. Okay? So these are the formulas that we're going to use. The word that's called non-volatile, spelled volatile wrong. Non-volatile. That's going to be a word you see a lot. So I just want to explain what that means first. So calculating temperature changes for boiling point elevation and freezing point depression will both happen from these formulas. You don't write down any other formula, write down this one. This is the most general formula, but it is exactly the same as these other two. I just have a little subscript down there to say, oh, boiling point or freezing point, to say specifically which one we're talking about. This is the one I will always kind of write down and then we'll adjust it if it's freezing point or boiling point. I keep right there. Boiling point. I scroll down just a little bit? Actually, we'll do that together. Okay, so I'll start here and we'll work our way down. So listen to the important stuff up here. We already talked about covalent, I is equal to 1 molecule. We also call covalent non-volatile covalent compounds because, you know, if you put, let's say, acetone or something really, like vinegar, something really smelly into water, it's going to be vaporizing a lot. The vapor pressure isn't going to lower. So we try to find non-volatile covalent compounds like sugar. Does sugar evaporate out of water? Not really. Then all the sweet tea would be no longer sweet, right? It doesn't vaporize. It's a solid, not like alcohol or something really volatile. Okay, so that's just a word we use a lot. Ionic, we said that we're going to be using the ions, so the electrolytes, but we're also multiplying the molality by that. So we did that molality question this morning because you'll notice there's a little m in the formula, which means molality. So this is the general formula. I call it Chem. Delta T is equal to Chem. The K, the little k, is based on the solvent. So you have to be very, very, very careful with which K value you're using. It's a constant though. You will always have that constant unless I'm asking for you to solve it for it based off like the formula equation given. So it's the same formula for both scenarios. It's just the K values are different. So I can find the delta T, the freezing point temperature change, by using the KFP freezing point. It's called something. It's called the Malau freezing point depression constant. That's what KFP stands for. That's a really long name, so I just go KFP. So it's called the Malau freezing point depression constant. So what do you think the KBP means? The Malau boiling point elevation constant. It's the same thing that we've been talking about this whole time, okay? So I don't differentiate between these two, just that it's boiling or freezing, but so we'll use the Chem one often. This delta T though is in degrees Celsius, just like our delta T was for heat, okay? So you write down this pages so you can use them if you need to later on, but we use water, probably 9 out of 10 problems, as our solvent. So I'm going to go ahead and tell you the ones for water, because they're very common to see. So the freezing point, the Malau freezing point depression constant for water is 1.86 degrees C per Malau. And the boiling point elevation constant, the Malau boiling point elevation constant for water is 0.152 degrees C per Malau. So we'll use those a lot. And we already did the ion, so we'll do like one more here. Let's do this one, calcium carbonate. How many ions does that make? 2. What 2 ions? Calcium what? Charge? 2 plus, and carbonate with a 2 minus. Okay, so there's 1, 2. I is equal to 2. Okay, so this is a good review of nomenclature. See how that works? Because you see your calcium and your carbonate, and they both had a 2, but they both reduced down to 1s. Empirical formula. All right, so let's do some practice ones together, and you guys will practice and get your stuff done. Okay, no, we just did this. Let's not do this one right now because we just talked about all that this morning. We'll come back to this. Okay, let's do math and then we'll come back to conceptuals. How much, so I'm talking about delta T, how much will adding 2.65 moles of sugar decrease the freezing point of 2.5 kilograms of water? So that's our first question. So let's write down our givens, just like we always do. What are our givens here? 2.65 moles of sugar. Okay. 2.5 kilograms of water. And what does it say I'm looking for? Decrease in freezing point. So I'm looking for delta T, decreasing freezing point is degree C decrease. And I'm going to put in parentheses freezing point so I remember that's what I'm dealing with here, okay? All right, so for colligative properties, what formula are you going to be using? So delta T is equal to K FP I M, right? So I just say Kim. Delta T is equal to Kim, okay? So the FP is just denoting the specific constant. All right, so do we have delta T? No. Do we have K? On your paper, right? What's K? What's the KFP for water? 1.86 degrees C per millal. Okay. What's the I for sugar? Why 1? Right. You see this big thing? Do you see any ions in there? Nope, not metallic at all, right? So this is covalent, so the I is equal to 1. I is equal to 1. Now, how do you get molality? Moles over kilogram. So I'm not even going to calculate molality. I'm good about putting this in my calculator, just as is. 2.65 moles over 2.5 kilograms. I mean, you can go ahead and calculate it separately and then plug that value in here, or you can just do it all at once. It's up to you, whatever floats your boat. So somebody tell me what your delta T is here. I recommend you doing some calculations with me so that you're comfortable with this on your own. What'd you get? Yeah. 1.9716 degrees C. If you carry it out a little bit. Okay, so that delta T is referring to what? What's it referring to again? Freezing point depression, right? Okay, so what was water's freezing point? What is it? 0 degrees Celsius, right? Water's normal freezing point is 0 degrees Celsius. We're subtracting the freezing point depression, so we're subtracting the delta T. We're subtracting 1.9716 degrees C. So what's the new freezing point? Negative 1.97. I'm going to stop it there, okay? So there is our new freezing point, negative 1.97. That's pretty good. It doesn't get in the negatives real often in North Carolina, so we're doing good. Okay, so let's do the same thing. I want you guys to do it for boiling point, though. Yeah.
So then, like, the final answer would be what the freezing point?
So the two final answers would be how much will adding decrease the freezing point? So the delta T is our first answer. And then the second question said, how will it change the boiling point? What will the new freezing point and new boiling point be? So I just went ahead and did the freezing point one.
Okay.
So these two are 2 of the 4 answers. So you guys do it for delta T for boiling point. Or maybe tell me what's different. The first number meaning the K number. Okay, so the K number is different. Is that it? Basically, right? Basically. Okay, so I'm going to go through this quickly. Our boiling point is so, yeah, where did I get this number, guys? Water's boiling point constant. You wrote it down on the last slide. So, I will always give you those values. Do not memorize them. Okay, that's awesome. I mean, you might accidentally, but, you know, that's cool. All right, so once you plug in your boiling point, KBP, your I factor of 1, because that's what all covalents are going to be, and your molality, and I don't know, you can leave it like that. That's fine. You get your boiling point increase or elevation to be this. So how do you get the new boiling point of water? Take what? So 100 is its current boiling point, so normal boiling point, and you're going to add the difference because it's elevating, it's increasing. 0.5427, right? So the new one is 100.54 degrees C. So if what freezing point gets compressed, you subtract. Boiling point is elevated, so you increase it. All right, there's one more down here. We're going to do salt, road salt, which is sodium, or not road salt, normal salt, sodium chloride. You guys do the same thing for this. Number 2 here. Yeah, I will scroll up. You guys can see some of the variables are similar. Nathaniel, give me a second. Oh. There you go. So you guys do this one. Salt. Let's go. Alright, you guys got this. I'm gonna write it up here too. What's the I? What's the formula? Let's go formula first. Sodium chloride. NaCl. It breaks up into Na plus, Cl minus. So what's the I? 2. That's the difference here. What's the molality? Does anybody have a value for it? What is it? 1.06 molal. Okay, so this one actually, I want to show you how your units are canceling, because molal is that unit, that little m. So little m here cancels with little m that's here, leaving you with degree C, which is, you know, what delta T is supposed to be anyway, so we're good. What you get for your freezing point depression? What is it? Okay, so there's our delta T for freezing point. So what's the new freezing point of water? Right, and so you don't have to show me 0 minus delta T. Like I know that you can do that right in your head. So you can write just new FP, new freezing point, negative 3.94 degrees C. I know you can subtract from 0. All right, so then how do you get the boiling point elevation? So boiling point, 0.512 degrees C per molal times 2 times 1.06. So you should be seeing that if I don't change the moles of solute or kilograms of salt, the molality is the same. The constant will change based on what you're talking about. And the I factor is going to change based on the type of substance, right? Or how many particles it makes. So what's this freezing, or what's this delta T? 1.0085 degrees C. So what's the new boiling point of water? 101.0. I'm going to go 09 just to round up there, because I think we probably have too many sig figs here, but it's better just to show you all your work there for me, okay? Yeah.
Where's the 1.06 one? Like, why is that?
Somebody calculated what 2.65 moles over 2.5 kilograms was, so I didn't have to write those out as a fraction anymore.
Oh, so it is the same thing as the other one?
Yep, all the variables were the same except for the identity, right? Okay, so based on your calculations, Which has the greater effect on water? Which one? No, which one? Which substance? Sucrose or salt? Salt, right? So ionic is always better than covalent, okay? So in this case, sodium chloride had made a bigger impact, more significant delta T than the sucrose sugar, okay? And so based on that knowledge, which of these is going to change the boiling point the most? Which of these? Maybe you should write the formulas for that. Well, here, let's write out the formulas, because in a process like this, like if I give you multiple choice question, I was like, which of these changes the delta T the most, or the boiling point the most? You probably want to write out the formulas so you can identify them as ionic or covalent, yeah? Okay, and their I factors. What is this? Okay, so you saw tetra there. That's screaming at you that it's ionic or covalent. Covalent, right, covalent. You only use prefixes in covalent substances like carbon dioxide or carbon monoxide, right? So this is covalent. What is the I factor? What is it? 1. I factor for covalents are always 1 because that crap does not break up. They don't. It's a molecule. It stays together. It looks like this. Cl, 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 Cl with dots, you know, for octet. Okay, so there you go. That's covalent. This one, formula. Okay, NaCl, it's ionic, Miss Inlow, thanks guys, and I is 2. Okay, this one. Al2O3, ionic or covalent? Ionic, okay, you knew it because it's got a metal involved, right? So ionic, how many does this break into? 5. I of 5. So if you don't go down that far, you don't tell me your I number, you probably won't get this right. So which of these is most influential on the boiling point? Aluminum oxide, right. So because it's got 5, the I factor is 5, it makes the biggest difference in chem. All right, cool. So let's go ahead. Oh, I'm not going, well, I'll show you this. This is the phase diagram. You guys remember seeing this? Solid, liquid, gas? Remember seeing these? This is just a graph that shows you solid, liquid, and gas. The differences in boiling points then from normal versus the solution form. So in purple, this color, pink is our normal curve, and you can see that the curve backed up to show that the difference between solid and liquid. Well, what's the physical change between solid and liquid? Melting. So what's the opposite of that? Freezing. So it's showing you the freezing point is pushed back, and that temperature down there is decreasing, right? So you can see that the delta T there is shown on a graphical form. And you can see that over here, the boiling point, so from liquid to gas, is boiling, right? So you can see that the purple line moved over to this blue line, so the boiling point was increased and the freezing point was decreased. So you can see that graphically as well. You can actually read a graph and get the delta T's. Okay, so your job is to do, I think I've got 6 or 8 questions here. 8 questions. You guys have those for your lecture notes. You have the rest of the time. I have an article we might get to. So I'm going to say let's go for 30 minutes right now. The only word I've not mentioned yet is Van 't Hoff factor. I'll write that at the top. Write this word. Van 't Hoff factor is what I've been calling I. It's just basically the I factor. So when I say I factor, I mean Van 't Hoff factor. That's just the guy's name. So if you ever see something on your homework, it's like, what's the Van 't Hoff factor of sodium chloride? I just mean, what's the I factor? What's the I? So it's just number of particles. One thing I didn't tell you. Alright, so calculate, have problem set 15, 16 out after you finish your lecture problems. Finish those on problem set 15, 16. Okay? Yeah.
Can I get the picture of the lecture notes?
It's on the corner on the table over there. Please ask me questions as you go, and I'll put the answers up shortly. I see yours.